Now other two components of a communication system are optical source and detector. If you find in this timetable, we have given a one slot for optical source and optical detector. Reason being, optical sources and detector, they always remain in a very comfortable environment in the telephone exchange, whereas all the environment problem are to be faced by the optical fiber. Optical fiber is in the field, so whatever problems we had in a communication system, these are with the optical fiber. So it's important to understand all the mechanisms that lead to degradation of the transmission characteristics of the optical fiber. Optical source and optical detector, of course, they are very important. Unless you have a very good detector, very good source, so that I am able to efficiently couple the output, the power of the from the source to the optical fiber. Similarly, I need a very sensitive detector. Detector with very high sensitivity, because we also discussed the power levels in the optical fiber is not very high. It is of the order of milliwatt. In order to avoid the non-linear effects, the power levels are kept low. As a result, we have there is attenuation in the optical fiber, and at the detector, very small amount of the power reaches at the destination. So communication is only possible if I am able to detect the signal at the destination. So as a result, we need a very sensitive detector. So they are either pin detector or APDs. APDs, these detector, they can detect power up to the level of microwatt or even nanowatt with the APDs. So today's session will be on optical sources and detector. For this session, we have with us Sri Randhir Bhatnagar. He is senior scientist at CSIO, working in the area of optoelectronics or photonics group at CSIO. Dr. Bhatnagar, he has vast experience working with these optical devices. They are designing different type of optical communication systems and optical sensors, where we use the optical fiber, we use the light sources, we need that very powerful detector or interrogator for any sensor. So he will discuss regarding the optical sources and detector, their compatibility, mostly with compatibility with the optical fibers, because I need a we know optical fibers are very thin, of the order of micron size. Similarly, our detector has to be of that size. The compatibility is the main criteria for these optical sources and detector. And again, we discussed, we use the multi-mode fiber, we use the single mode fiber, and we discuss the dispersion, broadening. So broadening, all these parameters, they depend upon the line spread of the source. So smaller the line spread, smaller will be the dispersion. So I'm thankful to Bhatnagar ji for accepting my invitation and be with us for sharing his experiences while dealing with the devices. So I request Bhatnagar ji to start the session.
Very good morning to all of you, and thanks, Dr. Chaudhary. Today we will be discussing optical sources and detectors. As Dr. Chaudhary has said, these are the main elements in any communication system, any optical systems, because we need light. Because light is to be propagated, light is to be sent to the media, and then it is to be detected the form, which form the light source is coupling to the fiber or to the system, and we are detecting the attenuation in the fiber, the attenuation in the light. It can be in an amplitude way, it can be in a phase way or a frequency way. That means there should be some detection mechanism which could sense this. So today we begin with this optical source and detectors. So the emission of light or optical sources is in the form of a photon, which can be either spontaneously emitted or stimulated emission. Stimulation and spontaneous emission we will discuss after few slides. For spontaneous or stimulated emission to occur, the energy must be supplied, because I want these photons to be emitted. The source is nothing but, light source is nothing but, it is emitting photons, right? the photons are emitted when I supply something to them, right? The energy can come from many sources. It can be a heat form, it can be incandescent light lamp, like we have this type of lamps, electrical discharge lamps, which is deuterium, sodium, and mercury lamps, or it can be electrical current, which is laser diode or LEDs, or bioluminescence. Bioluminescence is fireflies. It creates also lights. So there are many ways whereby I can create lights using these mechanisms. The basic is that I have to excite the electrons to a higher energy state, de-excite them to emit the light, or recombine them with the holes to create a light. So based on this phenomena, the sources are finding applications in analytical instruments, communication systems, industries, automotives. The basic type of optical sources are tungsten lamps, deuterium lamps, mercury lamps, hollow cathode lamps. These are used in analytical systems or your automotive systems, and optical sources which are typically used for fiber optic systems, either in communication or in analytical systems. They are LEDs and laser diodes. Within the LEDs, we have surface light emitting diodes, edge emitting LEDs, and superluminescent LEDs. And then under these laser diodes, we have distributed feedback lasers and DBR lasers, distributed bragg reflectors lasers. We will be discussing one by one all these concepts of LEDs or sources, why we need so many varieties of sources within LEDs, within laser diodes, why we need that. So basic requirement for the performance for any fiber optic system or any analytical system is its compatibility. Its compatibility with the system. No? It can be a fiber system, it can be a analytical systems. That physical dimension of the LEDs or source should match to the optical fiber, because the course is on optical fiber. So it should suits to the physical dimension of the fiber. The radiation pattern, because the fiber dia, the core dia is of the order of 8 to 10 micron for single mode, or 60 micron, 62 micron for multi-mode. So it should match the emission pattern of this source should match the dimension of the optical fiber. That means it should be narrow radiation pattern. There should be linearity. When I supply current to this, the output should be in a linear fashion. So to avoid the nonlinear phenomena. Then the ability to directly modulate this, because I want a modulation phenomena to take place on the light which I made it to propagate through the fiber, right? It can be analog modulation, it can be a digital modulation. If it is linear, then the modulation is linear and I can detect in a linear fashion. Otherwise, non-linear components will come in. Then fast response time, that means when I change the current, it should immediately switch on or switch off, either in a analog fashion or in a digital fashion. Adequate power output, I should be in a position to couple this to the fiber. Narrow spectral width, that means the amount of wavelengths or the bandwidth of the wavelengths, it should be narrow, because dispersion effects will come into that place. Then stability and efficiencies, driving circuit issues, reliability and cost. All these phenomena, all these parameters one must consider while selecting these sources, which can be a laser source or it can be a LED source. So coming back to the LED operation, what basically LED it is basically a PN junction diode, and then we have on the conduction bands we have electrons, we have holes on the valence bands, and then we supply the energy to push these electrons to the conduction band, because they are at a higher energy states, though they fall back to the valence band and recombine with the holes. During the recombination process, they emit the light output. This light output is based on the band gap energy of the particular material. So based on this band gap energy, it emits a particular wavelength. So by changing this band gap, we can change the wavelength emitted out of this LEDs, right? Choosing different materials, it is possible to select the wavelength output from this. So not all electrons hole recombination will produce the light output. It can be a heat also, right? So I call it as a radiative when it produces a light output, non-radiative when it produces a heat phenomenon, a phonon, right? So this is basically a simple LED operation. So what we need a PN junction diode, and then it is forward biased to push the current to the P junctions, and then it recombines, the electrons and holes recombines and produces the light output, right? Emitted wavelength depends on the band gap energy, and transition takes place from energy in states in either band, because when we say conduction band, it is not just one discrete band, it is a band. It carries different energy levels. Same way the valence band also carries different energy levels, and then when it transits from one band to the another, from one energy state to the another, it emits a wavelength. Because if this band is not a discrete one, single band, it is a multiple of energy states. That means it can emit a number of wavelengths based on the band gaps, right? So it produces a spontaneous emission. It produces a band of wavelength output from the LED. So it is an incoherent source, plus it produces a band of wavelengths. What we need in the communication systems, a single mode output, right? A single wavelength output, because dispersion effects takes place, because each wavelength will travel with its own velocity, right? So if I send a pulse to it, and if that pulse carries a number of wavelengths, so it spreads out at the detector end, right? So what we need, that the source should be such that it produces a single wavelength, a monochromatic wavelength, a large output, right? But while considering the options, what is available to us, what we can do further. So one option is LED. LED gives a incoherent output, a band of output which is carrying number of wavelengths, and it is based on spontaneous emission because it's a random phenomenon. So the different materials which are being used to produce this different wavelengths, like for this wavelength, 0.9 wavelength, micron wavelength or 900 nanometer wavelength, gallium arsenide based LEDs is being used. For the next generation, second generation, indium gallium arsenide, which caters to 1.3 micron, 1300 nanometer. Indium gallium arsenide phosphide, it caters up to 1.7 micron or 1.5 micron also for the third generations. And these are the band gap energies of different these materials, right? So as we see in the last slide, that the P and N junctions, they are of the same materials. I can use gallium arsenide P type, I can use gallium arsenide N type, combined together, a band gap, a depletion layer is formed, and when I push it the current through forward bias, it creates a recombination process, and then it produces the output wavelength. So this is the basic operation, that you have a P-type material, you have a N-type material, you have the active region, and recombination takes place in the active region, right? So this recombination produces the light output. Now you can see this light output is coming out from all the directions, right? So what we need, I want this light output to be coupled to my media, outside media. My fiber is at a one point, right? It cannot be at all the points. So what I need, I must confine this active region to a narrow region, so that I can couple maximum output to the outside media or fiber, right? So the light is emitted at site of carrier recombination, which is primarily close to the junction, which is called active region. However, the amount of radiated recombination at the emission area within the structure is dependent upon the semiconductor material used and the fabrication of the device. What is the junction area I have created during the fabrication is more important to me, right? For the simple case of LEDs, the junction area or the active region is much wider, so I cannot couple much light out of this LED junctions. It emits incoherent light because it is emitting from the spontaneous emission, which is not coherent, and it can be this type of LEDs or source. I can make use of up to 100-200 megabits per rates, which is now this type of LEDs is producing spectral width, because as I said, they are not discrete. The conduction band and the valence band, they are not discrete. It has all energy bands, and when this recombination takes place, it produces different wavelengths within the band. So for 850 nanometer gallium arsenide or aluminum gallium arsenide material is being used. For 1550 nanometer range, indium gallium arsenide phosphide or indium phosphide is being used. So as I said, this p and n type material, they are of the same material, so I call them as a homojunctions. This p material is also gallium arsenide, this n type is also gallium arsenide, and we have the active region in this region, right? And if I see the refractive index profile of such a material at the active region, it comes out to be like this. So it creates a tunneling effect, it creates a propagation effect within this region, right? Within this region, and it emits the light through this region. Now what we need, LED should have a high radiance because I want more light to be coupled to the fiber. At the same time, it should have a fast response time, it should have a high quantum efficiency. When I say quantum efficiency means how much current I am pushing in, how much light I am getting. That defines my efficiency of the LEDs, right? So now the question comes, if it is giving me output on the all sides, what I should do, what fabrication aspects I should look into, so that I can get the confined light. The carriers are confined, the light is also confined, right? So here what we now look for a heterojunction devices, right? We use different materials so to create a heterojunctions, so that we can confine the light in a proper way where we want this light to be coupled to the fiber. So a heterojunction is an advanced junction design to reduce diffraction loss in the optical cavity. This is accomplished by modification in the material to control the index of refraction of the cavity and the width of junction. So basically what I want, now the junction width I must control, right? So secondly, the carriers, the photons which are propagating, it should confine within that junctions, right? So if I create a refractive index profile within the junctions, so it is possible. Like we see in the fiber optics, we have a core which is high refractive index, we have the cladding which is low refractive index, and the core is confining the light. So same phenomena one can look in the active region also, that if within the active region, within the depletion region, I create a high refractive index profile centered by a low refractive index profile at the outer edges, so that the light is confined within that profile, right? So this is the basic phenomena required for heterojunctions. So that same thing is to be fabricated in the semiconductor material. Let's see one by one. The index of material, refraction of the material, depends on the impurity used and the doping level. What doping level I introduces, what material I introduces, the refracting level index is defined by this. The heterojunction region is actually lightly doped. The center portion, which is having high refractive index, is lightly doped with p-type material and has the highest index of refraction. The n-type material and more heavily doped p-type material both have lower indices of refraction. So if I dope lightly, it has a high refractive index, it has a low refractive index. If I dope other way around, it has a high refractive index. So this produces a light pipe effect. That means I can confine my light carriers within that region of high refractive index to the low refractive index. So in a homojunction, however, this index differential is low and much light is lost. So in this situation, a double or single heterojunction is possible with better light outputs. So let's see this, that we have a p-type indium phosphide, we have a n-type indium phosphide, and then we have sandwiched another material which is n-type indium gallium arsenide phosphide. Now this creates a junction. It creates a heterojunction at this point as well as this point. So there is a double heterojunction at this point. Same situation one can look for a single heterojunctions where you have a p-type material of gallium arsenide and n-type gallium arsenide and aluminum gallium arsenide. So there is only one heterojunction which is available here. If we see the refractive index profile, we see that there is a confinement of carrier at this point only. We have a high refractive index profile, we have a low refractive index profile at both ends. That means the carrier is now confined using a light pipe effect. So heterojunction is a junction between two different semiconductors with different band gap energies. Now this band gap for this is different and for this two are different. The difference in band gap energies creates a one-way barrier. Charge carriers are rotated over the barrier from the material of higher band gap energy to the one of lower band gap energy. So when a layer of material with a lower band gap energy is sandwiched between material with a higher energy band gap, a double heterojunction is formed, right? This is called double heterojunction because there are two heterojunctions present, one on each side of the active materials. The double heterojunction forms a barrier which restricts the region of electron hole recombination. Basically, we want the electron hole recombination to be confined so that the light output which is coming out is also confined within that different refractive index profile. So this region is called the active region. So let's see now what is double heterojunctions. We have a N-type indium phosphide, we have P-type indium phosphides. The band gap of both these indium phosphides are same. It is 1.35 electron volts. This is also 1.3 5 electron volts. And N-type indium gallium arsenide, the band gap is 1 electron volt, right? But the valence band of this is much lower as compared to this, right? Same way, the conduction band of this is much higher as compared to this. Same is the reverse situation over here. That means now I can push, if I forward bias this, I can push electrons from here to a lower end. Same way, I can push holes from here to this region, right? So there is a barrier exists over here. There is a barrier exists over here. That means now I confine my electron hole recombination within this region, right? So if by some means I created a sandwich phenomena here, so I can create the recombination process to be confined within this region. Now the refractive index profile, if I see, the refractive index of this and this is around 3.2, and the refractive index of sandwich layer, which is active layer, is around 3.5. That means now I have created a high refractive index profile in the center of the active region, right? So that means the recombination, the light tunneling is also confined within this region, right? So that's the advantage of double heterojunctions. So the valence band of N-type indium arsenide is at a higher energy level. This valence band is at a higher energy level than the valence band of the adjacent N-type indium phosphide. The conduction band is at a lower energy level. The conduction band of this material is at a lower energy level, so as to confine that. So if now we have to fabricate this, right? We need to fabricate such type of material. So what we need a N-type indium phosphide, we need which is a substrate layer, and this N-type indium phosphide and P-type indium phosphide is called a confinement layer. Don't go back. So this and this, they are called confinement layer, right? They are confining the electron hole recombination within the active region, and this is called the active layer. So this is now a confinement layer we have fabricated, and now we have the active layer here, N-type indium gallium arsenide phosphide, and now the active region wherein the recombination process takes place, and then we have the electrical contacts and the heat sinks. Then we have the insulators here. By proton bombardment within the silica, we can create a insulator. That means the current will not flow, the electrons will not flow on these sides. So we have created a symmetry, a sort of a cavity within this active region, which confines my electron hole recombination and the light output. So the material in the active region has a higher refractive index than that of the material surrounding it. This means that a mirrored surface effect is created at the junction, which helps to confine and direct the light output, right? So this is double heterojunctions, wherein the number of materials has been used to confine the light. We have the metal contacts, we have the N-type gallium arsenide, and the reverse is here, metal contact P-type gallium arsenide. We have P-type gallium aluminum arsenide, which is a carrier confinement layer. This is also carrier confinement layer. We have a recombination region, which is of the order of 0.3 micron. So during the fabrication process, we have to confine that symmetry, which is 1 micron here, 1 micron here, 0.3 micron. The width of the junction is this. And if we see this refractive index profile, we see there is a high refractive index region existing at the recombination region, which confines the electron hole recombinations. So within the device, the light must be confined and direct it to the exit aperture. Basically what we want, the confinement of the light within the active region to a narrow region, and then the light output should be higher, so that it can be directed into the fiber, which is done using insulating material silica to confine the active region and current path. The active layer in a heterostructure has a higher refractive index. This junction forms a mirror layer, helps to confine the light to the active layer. For this reason, the outer layers are often called a confinement layer. Now, once we created this structure, we need to couple this light to the fiber. Now, the refractive index profile of the semiconductor is of the order of 3.5 or 3.2, right? Whereas the fiber is around 1.5, 1.45, right? That is the refractive index difference variation. Now, I need to couple that light to the output end, right? So, the amount of cost involvement in coupling is much more than to the fabrication of the semiconductor device. So this is how one can couple. There are 4 ways that one can couple this light output to the outside fiber using a grain lens, which is gradient index lens. That means the light which is coming out of this junction is focused through a refractive index profile media or through a lens to the fiber output, or I can use a spherical ball to couple the light output to the fiber, or I can directly push this fiber to the junction area wherein the maximum light I can couple, or I can create a lens at the fiber end itself. I have created if I have take a fiber and grind it so that a lens is formed at the edge, so I can couple light output from this region, right? So these are the 4 mechanisms by which I can couple the light output to the fiber. So one is gradient index lens, another one is ball lens. Now all these lenses I must use a epoxy so that I can jointly couple this. So direct coupling method, wherein I can push the fiber to the surface so that it touches the LED directly. That is to mount the LED inside a connector, so that when a fiber is plugged in, mounted in the outer half of the connector, one gets firm mounting in a good position so that I can couple the light output. Another one is I can create a lens within the fiber itself. Now once I have defined a heterojunctions wherein I am confining the light, I have coupled the light from these heterojunctions through the fiber using lens phenomena, right? Now what next is it structures. What type of structures within the heterostructures is possible using this double heterostructure possibilities. One is surface emitting LEDs, which emits light from the surface. Another one is edge emitting. From the edges I can take the output. Another one is superluminescent LEDs, which is high power LEDs, giving me much better light output. So confining and guiding the light is one of the challenge. Once you have the LEDs, guide the current flow to a small active region, guide the light produced out of the device into an easy position for coupling to a fiber. Let's see one by one what these LEDs are. See, once we know, if we want to develop some systems based on fiber optics, wherein we need to use sources or detectors, and in the market so many varieties are available, then one must know what one must select, whether SLEDs, ELEDs, SLEDs, or laser diodes. Within the laser diodes, which one? What is my requirement? So one must understand the specifications, the features involved in each of these LEDs or laser diodes or detectors. So one by one I am taking all this. So surface emitting LEDs is nothing but it is again a double heterostructures, but the light output is coming out from the surface, from the top of the surface, so that I can couple fiber up to this point either through a ball lens or through a etching a lens on the fiber surface itself. So I can push that lens, I can push that fiber right on the top of the surface. So method for obtaining high radiance, basically idea is to get the high radiance and to get the minimum bandwidth, the minimum wavelength output, is to restrict the emission to a small active region within the device. And Burroughs in 1970 has fabricated this device. So power coupled into the fiber is dependent on many factors: distance and alignment between emission area, what is the distance between the fiber and the emission point, emission pattern, what type of pattern it is emitting, whether it is a parabolic or simple light line side, or interfacing media. What we need, but this type of LEDs gives more power but poor radiance. That means the output in a single solid angle is less. Coupling lens is used to increase the efficiency. For short optical links, I can couple this light to a large numerical aperture multi-mode fiber dia can be coupled to this. So again, the concept is same, that you have the active region, you have a double heterostructures region, and then you have a confinement layer. These are the confinement layers, and this is the active regions. So this type of surface emitting LEDs is possible using this type of structures. You have a double heterostructures, you have the active region here, and then directly taking the fiber right on the top of the active region, so that I can couple maximum light output from this. And this is the bonding material, and during the process itself we have etched the circular edge, so that my fiber or lens can go right into the active region, which is of the order of 0.3 micron, roughly 300 nanometer, right? So surface emitting LEDs is also known as burst LEDs in honor of C.A. Burst, who has developed it. The type of active region is available is of the order of 20 micron to 50 micron, whereas the single mode fiber is of the order of 10 micron core, right? So I cannot couple single mode fiber to this type of LEDs. So I need a multi-mode fiber which can be coupled to this. The primary active region is below the surface of semiconductor substrate, perpendicular to the axis of the fiber. A well is etched into the substrate to allow direct coupling of the emitted light to the optical fiber. The etched well allows the optical fiber to come into close contact with the active region, so that I can couple the maximum light. The another option is, one is from the surface I am coupling the light. Another option is, can I couple from the edges, right? So another area, again the concept is same, that you have a double heterostructures. These are the two light guiding layers or confinement layers, and this is your active layers. Within the active layers I have created a stripe. So think of a situation that I have, during the fabrication itself, I have created a strip like this. So it is just going like this on the active region. That means I am confining the cavity. I am building a cavity within the active region. So basically it is the cavity which carries the modes, which carries the wavelengths. Different wavelengths are exited because of from the cavity itself. So dimension of the cavity, if I minimize, so I'll restrict my narrow bandwidths, right? Basically the wavelength which is coming out of that I can restrict. So the output which is coming from the edges is again Lamarckian. It gets exited in this direction as well as in direction. So it carries a wavelength parabola like this, right? Both dimensions is possible. So concept is same. It is again a double heterojunctions. We have a active region, again active region. We have a silica here, which is confining the electric current to be flown only in this region. And then we created a heat sinks, so that I can dissipate the heat because of the current which is flowing through this. However, this has slightly better advantage, because the divergence of the beam I can control. Secondly, a small numerical aperture fiber, single mode fiber, I can couple to this, and it has a lower spectral bandwidth as compared to SLEDs. Huh? slit part. This part, huh? So basically, in simple LEDs, we have the active region which is all around the surface, and the light is emitting from all directions, right? So what I want that active region should be confined, right? So one is I can confine from the top surface. I can restrict my confinement to this so that I can get the output on that side, or I can confine along the length of the junction, right? All along the length of the junctions, right? So basically the confinement of this light is within this region, right? Right? Okay. So let's see, I have a cavity which has a this width, this height, and this length, right? So there are many ways a light can propagate. It can jump like one way, or it can take like this. Same way it can take like this, no? Like this. So that means there are many ways a photon can propagate within the cavity, isn't it? And the each way leads to a different wavelength, right? When I want a wavelength to be confined, the output of the LEDs to be confined, basically dispersion effect I want to be minimum. So for that reason, I must confine this cavity. So there are many ways I can confine that. One, using on the surface, another using all along the line, and then created a strip here. Think it is not possible to see from here. You think that you have a rectangular piece. On the rectangular piece, I have created a cavity. So this strip which is going in, which is shown on this side, is also available on this side also. So basically, I am reducing the dimension of the active region. I am reducing the dimension of the cavity itself. So that by I am creating a narrow spectral bandwidth. At the same time, I am confining the electron hole recombination to a confined layer, right? So that the light output is now maximum available to me, right? And these are insulator layers. This is all insulator. That means my electron holes will not transport to this region. They are all available within this. So I am confining my recombination process within the active region to a very narrow region. So the maximum light output I can get from that region. Clear?
So the insulator must
Huh?
have
Huh.
the insulator region must have the high refractive index in order to guide the photon coming out.
No, the high refractive index is the active region. This region is, say, fiber. How fiber works? The fiber has a core which has a high refractive index. It has a cladding which has a low refractive index. So the total internal refraction takes place within that core. That means I must have a high refractive index at the center and low refractive index at the outer edges, right? So basic idea is, once you have a LED, what fabrication process I should look for, so that I can find my light to maximum efficiency. I can get the minimum spectral bandwidth, so that my dispersion effects or the monochromaticity of the source I can achieve better, right? So in that process we have SLEDs or EE-LEDs as emitters. So next comes the superluminescent LEDs. Now think of a situation, we have a structures, again double structures. In case of laser, we'll discuss in the next few slides. We have a laser where stimulated emission overpowers the spontaneous emissions, right? And then we have the mirrors. The edges are acts like a mirror, wherein the beam keeps on oscillating to provide a gain media. Now think of a situation, if these two mirrors are not parallel, slightly tilted, right? Now the gain will not come, yeah? Because in an ideal situation where laser phenomena takes place, these mirrors should be parallel. If by during the fabrication process, think of a situation, one mirror is slightly tilted, right? Now the oscillations will not take place, but stimulated emission will take place, right? Gain will not come, but stimulated emission will come, isn't it? So superluminescent LEDs are nothing but a sort of a laser diode wherein the mirrors are slightly tilted. During the fabrication process, it is not possible to align them. So we have the stimulated emission within the setups, within the active region, and then it produces a high output. Rather than spontaneous emission, stimulated emission gives me larger output and plus coherency. Right? It has a slightly better coherency as compared to LEDs, but lesser as compared to laser diodes, where the mirrors are parallel. So this is another area we have seen during Deepavali time. These LEDs, very bright LEDs are available in the market. And they are nothing but superluminescent type, where during the process we are not in the process to maintain the alignment of the edges. So it gives me directional output beam, very high power output, and narrow spectral bandwidth of the order of 20-30 nanometers, whereas LEDs gives me 80-100 nanometer bandwidth. So again, we need a forward bias double heterosexes. All these phenomena are same. So superluminescent has a edge emitting LEDs based on superluminescence. It combines the high power and brightness of laser diodes with the low coherence of conventional LEDs. Emission bandwidth is of the order of 5 to 100 nanometers as compared to LEDs. LEDs, LEDs between the uh, no, no. See, basic phenomena is you have a PN junctions. Within the PN junctions, you have a spontaneous emission, stimulated emission, and absorption. All three phenomena are taking place. In case of LEDs, it is spontaneous emissions. It is not stimulated emissions, right? I'll cover that stimulated emission, what it is exactly, right? Next, just wait for 2-3 slides more. So once I need to compare what SLEDs or ELEDs is. SLEDs gives me slightly better bandwidth. ELEDs gives me slightly confined spectral bandwidth. SLEDs gives me more output, but ELEDs gives me slightly lesser output, but it is more coherent, and I can confine it to single mode, whereas this I can confine it to multi-mode fiber. Right, so this is what comparison is. If I see the LEDs, the pattern of output is of the this type. It is Lambertian types. It is not single beam. It is of this type. And now, if I want a fiber to be get coupled, that means I must tap to this point. I must tap maximum output so that I can confine my light output to the fiber coupling. Now the output of light, versus the current which I feed in is a linear functions, right? So as I keep on giving the light, keep on giving the injection current through the forward bias, the light output also increases. The light output also increases linearly. So LED is forward bias, its current increases rapidly and must be controlled by to prevent the destruction of device. That means I must place a resistance so that the current which is flowing out of that should be restricted. Now these are the parameters which I must consider while selecting the LEDs or a source for my communication systems. Full width, half maxima, what is the maximum intensity, what is the bandwidth available to me, peak wavelength wherein I want to work, forward current, what is the value of current which I look for, whether I need a heat sink, whether I need a high power transistors, rise time, what range of modulation signals I look for, whether this LED can modulate to that region or not, luminous intensity, that means flux which is coming out, or LED radiation pattern which is of this shape, what is the radiation pattern coming out of it. So all these parameters one looks for in the specification sheets. So it gives me a quantum efficiency. For a simple LED, it is of the 50% type. That means if I supply a 1 ampere current, it gives me 50% output of that. Same situation for a double heterostructures, it gives me 80% output, right? So that is what I look for. Okay, the cost of fabrication, all those things goes high, but I need a larger output. Then one defines the internal quantum efficiency, which is radiation of ratio of radiative recombination rate. That means how much recombination which produces light to the total recombination rate, which carries the heat as well as light. So that gives me RR into RT. Now RR, which is recombination rate, is related to your efficiency to the RT, and which is nothing but RT is nothing but I by E. What is the current I fed in to the number of electrons which is produced. So this gives me the recombination rate is related to your current and to the quantum efficiency. So the power output is nothing but your recombination rate to the h nu, which is energy of a photon, and this RR is nothing but IE h nu, which last slides gave me. The power output is now related to your current, right? So a linear relationship between the optical power generated in the LED and the drive current into the device exists. That means I can modulate my light output by modulating the current. We have seen in the during the Pavli time that we can modulate the LED output. The same situation can be modulated with my digital signal or analog signal to high speeds. So all these parameters I must consider. So for surface emitter, the light output is slightly higher as compared to the ELEDs, which is slightly lower, but it is more confined, more spectral bandwidth is less here. And both are linear at moderate drive currents. Now this output is also temperature dependent. The junction temperature, if junction temperature varies, the output also varies. So that gives me a feel. If the junction temperature varies, the output of this LED also varies. That means the Q point during the communication point, the quotient point of the at the receiver end, I must control that, isn't it? If I digitally modulate, then digital signal will keep on oscillating because of temperature effect, right? So you can see SLEDs are less temperature sensitive, LEDs are slightly more sensitive to temperature, and SLEDs are superluminescent diodes are more sensitive to temperature. That means while making for laser driver or LED driver, I must look for a temperature compensation also. That means I must look for heat sensing device within that system and control the setup itself. So that means I must look for thermoelectric coolers. We'll discuss later on the electronic circuit of that. So that means temperature output of LED will keep on shifting also because of temperature dependence of the junctions, right? The spectra tend to broaden with the increase in temperature due to greater energy spread in carrier distribution at higher temperatures. Not only this, the peak shifts, decreases, but it broadens and shifts to the higher wavelength. Increase in temperature affect the peak emission wavelength as well. Doping also affects. Based on the doping, I can see that lightly doped output is somewhere around 1.25, 1.3. If I heavily dope it, it will shift to the right sides. So increased doping level leads to increased line width also, right? And then we see the spectral line width for ELEDs and SLEDs. SLEDs gives me slightly bigger bandwidth, 125 nanometer. ELED gives somewhere around 75 nanometer bandwidth. So if I need look for a slightly more coherent or more confined output in the wavelength domain, then I look for ELEDs, right? And then superluminescent gives me slightly better, which is 30 nanometer. Right? The pattern broaden with increasing wavelength and are wider for surface emitters. So this is the drive circuits for LEDs. Simple. This is my LEDs which emits light. I can use a transistor which can switch much faster as compared to this analog input or digital input. I just transfer this output in the active region of this. When I make this transistor to switch on and off or within the active region, the current which is flowing through this will also change based on the analog input. It can be a sinusoidal, it can be a digital one. So this output will fluctuate. This current will fluctuate based on the base current, right? So that means when current is fluctuate, the light output, as I said, it is a linear function between the current and the output of the light in milliwatts. So I can control this. Now question comes, how to modulate, how to create more fast switching. Then I can look for emitter coupled logic or some higher techniques so that my transistor can switch much faster. And then the response time of this LED should be equally compatible to that, isn't it? Another domain is that you can use an op-amp, again based bias at the base, and then whatever the input which is available at this point. This point is fluctuating as per analog input, and so the light output also fluctuates. That's way I can modulate either in analog fashion or a digital fashion. Let's switch over to the lasers. Now, this as I said, laser LEDs is nothing but a incoherent output. That means the recombination is taking place randomly. There is no phase match or amplitude match. There is nothing like which I control there. So laser is coming in where laser is nothing but light amplification by stimulated emission of radiation. It gives me coherent light and narrow bandwidth or narrow beam width. It can produce high power output in communication applications. A laser up to 20 milliwatts or more are available, and a coherency and a percentage of light which I can couple is around 50 to 80% because it is coherent. So 50 or 80% is still much more as compared to my LED case. So there are three basic phenomena which takes place within the semiconductor when you take PN junctions. One is the absorption, that you have a light of a particular energy which is h nu. Now this energy is nothing but equal to energy gap between E1 and E2 bands, right? So the electron which is lying here gets absorbed this energy and rises to a higher energy state, right? Another phenomena, that once this higher energy electron is available at this band, conduction band, it decays back. It decays back based on the what is the holding rate of that conduction band. Right? It decays as its own time. So during decays, it emits the energy. Right? That is what is called spontaneous emission. Another phenomena, that you have a higher electron sitting here, and now you have a photon which is coming in. Right? So now this photon can stimulate this electron to go back to a valence band, emits the photon, and followed by the another photon which is already existing. So that means two photons is available to me at the output end. That is what is called stimulated emissions. So think of a situation that one person is sitting at the roof, another person is moving, giving a slight jerk, both moves out, right? So this is a situation. Now think of a situation that if I want a laser system to be made, I want that this to be overpowered by this phenomenon. That means when I stimulated emission is more as compared to the absorption, my laser emissions or my laser output is available to me, and this output is nothing but the wavelength which is compared to this band gap, isn't it? That means this wavelength is available. So think of a situation that if I place one mirror here, if I place one mirror over here, one is totally reflecting, another one is say 98% or 95% is reflecting, right? So this photon which is coming in is moved back because it is reflected, and it is again moved back, and if by some means I created more electrons here, so there is a possibility that I can create stimulated emission out of this. So that is the basics of this. So you have absorption, you have a spontaneous emission, you have a stimulated emissions, and now I need a two mirror to be created within these junctions to overpower the absorption phenomenon. therefore, what we need, that I need a population inversion. That means I must pump my electrons to the higher energy states by some means. So there are many ways I can pump it. It can be a light based, it can be electrical based, it can be a current based. So this process is called pumping, wherein I produces more electrons, more atoms at the higher energy state. So in stimulative emission, incident is stimulative photon will have identical energy, identical wavelength, narrow line width, identical direction, identical phase, identical polarizations. So the laser output is identical in all ways, no? Whereas in spontaneous case it is not. So that answers to your question, is it? No? When you say LEDs, this is spontaneous. There is no coherency between the output which is coming out. So basic structure is that you have two mirrors, you have a cavity here, you have a p-type gallium arsenide, you have an n-type gallium arsenide, and this is the active region. And now the light output is now making to and fro motions and creating a light output which is coherent, right? And then for this process, I need to pump in a current of the order of 10 raised to power 4 ampere per centimeter square. That is the area of that. And this junction is of the dimension of around 3 micron or so. So this is how another pictures shows that this is a spontaneous emission, which is going on all random direction, and this is stimulative emissions, which overpowers your absorption and spontaneous and gives you steady state laser output. And that is what, that you have a ground state atom, you pump the energy, it goes to the higher energy state, it decays non-radiatively, basically heat is produced slightly on this point, and then you have a stimulated emission taking place from the conduction band to the valence band and creating a laser amplifications. So same situation which we consider in the laser LED case, the same situation exists in the laser also. That means now we have a two type materials, homojunctions or heterojunctions. We again want a confinement, right? So there are varieties of lasers available within the laser system itself on semiconductor point of view. That means I want a light output to be again spot. A spot output, very coherent. I can create my cavity again on the active region. I can again confine my light using a confinement layer. So again, these surfaces are polished so that they become now a mirror to me. The silicon surfaces are polished so that they become mirror to me, and then the oscillations takes place between the cavity itself. The question comes now, I must reduce the cavity lengths, right? So this is Fabry-Pérot resonator, where this acts one mirror, this acts another mirror, and then you have this cavity which has this height, this width, this length, and based on this we have the different modes coming out of it, and this is the Lambertian output or Gaussian output of the light which is coming out from this spot, right? It can be in this direction or it can be in this direction, right? So if you see the laser beam output, it is spreading in this direction and it is spreading in this direction, but it is coherent, so it takes a longer path to get the dispersion to take place. So this is another schematic. This is the length of the laser cavity. You have 100% reflection, you have a slightly less than, so that a portion of the light output we couple. We are not coupling 100% light output, only 5% or 10% of the light is still enough to give me if I point my laser from here, I can see 100 meters away from the laser output. That's the output. And these are the modes which is existing between the cavity itself. Now these modes or the separation between the modes is governed by the width, height, and the length of the cavity itself. The question comes when I want a monochromaticity. I want only one wavelength. Question is, for my communication purpose, I want one wavelength. No? Because I want a dispersion to be avoided, isn't it? That's what my requirement is. One way is that if I, based on the cost, I can look for. I can look for a simple laser diode. I can look for a high cost laser diode or different varieties of laser diodes, which gives me slightly spectral bandwidth or monochrome opacity. So again, we look for heterojunctions. Within the heterojunctions, when I confine the cavity so that my active region, my carrier confinement is confined to a narrow region, then I need a lower current to be supplied. There was a time when we need to supply amperes of currents to the lasers. Now these lasers are available which can be operated on your cells, 1.5 volts cells. So the current reduces when we confine the cavity itself. So double heterostructures, injection laser diode fabricated from lattice matched of third and fourth alloys. Optical confinement on both sides of the PN junction, giving the injection laser a greatly enhanced performance. So again, the same structures, but we need two mirrors at the ends. We need two mirrors so that the stimulated emission overpowers the spontaneous absorption. So we have a P-type aluminum gallium arsenide, we have N-type aluminum arsenide, and we have P-type gallium arsenide, which is a low refractive index profile and is the active region. So again, the light output is from all the sides. Now I can create a strip between this to create a strip geometry. So these are all broader. I can create a strip here. I can create a strip here so that my cavity is now stripped to a narrow region. Right. So I am confining my both current carrier and photon carrier in that regions. And this region is silica oxide, which is insulator, right? So by bombarding proton on the silicon, it becomes insulator. So that's the another technique. So that within the silica fabrication, I can create insulator also. They are not conductive materials. So the stripe therefore acts as a guiding mechanism which overcomes the major problems of the broad area devices. So once I have created double heterostructures which gives me output from this edge only, but still it gives me some bandwidth, some spectral bandwidth, because there is a cavity and cavity has some dimensions. Now question comes, how to create a monochromaticity, how to get one wavelength out. When I say one wavelength, it is not possible. At the most I can say, okay, 50 picometer can I get, as compared to my 100 nanometer of LEDs, can I get 50 picometer from the laser? So what mechanism I should look for? Now think of a situation within this cavity, within this strip, if I create a grating during fabrication, if I create a grating, now grating will allow only one wavelength to pass. So that means within this mirror, I have one wavelength which is oscillating. So that means there is a possibility I can create within this laser, within this double heterostructures, a mechanism wherein I can get only one wavelength. When I say one wavelength is okay, 50 picometers or so. It has some band, but it's still slightly lower than as compared to this. So in this process comes the distributed feedback laser or distributed Bragg reflector, wherein a distributed feedback laser is a type of laser diode where the active region of the device is periodically structured as a diffraction grating. So the active region, I have created a diffraction pattern. I have created a diffracted grating on that surface. The structure builds a one-dimensional interference grating, which is Bragg scattering based, and the grating provides optical feedback for the lasers. The other wavelengths will not sustain, only that wavelength which matches to the grating period structure sustains, right? So DFB laser diode do not use two discrete mirrors. The mirrors are not required. Now the grating structure itself overpowers that. The grating acts as the wavelength selective element for at least one of the mirrors and provides the feedback reflecting light back into the cavity to form the resonant. The grating is constructed so as to reflect only a narrow band of wavelength and thus produce a single longitudinal wavelength. This is in contrast to a fabricated laser where the facets of the chip forms two mirrors and provide the feedback. Altering the temperature of the device. Now I have a 50 picometer at one wavelength. Now, if I change the temperature of this semiconductor junction, the pitch of the grating changes, because the thermal coefficient of the material itself. That means if I change the pitch of the grating, the wavelength which is selected earlier will change. That means now I tune it, isn't it? The wavelength which I look for, I can tune. By changing the current, see, one way is I can change the band gap of the material. That means I look for different materials. Now within the structure, if I change the current so that heat produces, and this heat will change the grating pattern or grating pitch, that thereby the wavelength which is selected is keep on changing. That means I created a tunable laser diode, tunable laser systems, which can be used for your gas sensing, your sensor systems, based on the tunability of the laser. So a change in refractive index alters the wavelength selection of the grating structure, thus the wavelength of the laser output produces a tunable diode laser. DFB are anti-reflection coated on one side, one is anti-reflective, another one is fully coated, highly reflective. In this case, the grating forms the distributed mirror on the anti-reflection coated side, while the semiconductor facet on the highly reflective side forms the other mirror. These lasers generally have higher output power since the light is taken from the anti-reflection side, and the HR side, or high reflecting side, provides the light output. So let's see the structure. You have the active region here, you have the confinement layer here, and on the confinement layer I have created a grating pattern, right? So this grating pattern gives me only one wavelength which sustains within the cavity. This is your HR coated, highly reflective coated. This is anti-reflection coated. So light output I have taken from on the sides, right? So only one wavelength will be allowed, of the order of somewhere around 50 picometer or so. So as compared to the LEDs or SLEDs output, or even laser diode output, DFB lasers gives me a slightly better monochromate output as compared to the other laser diodes or LEDs. Another options within this DFB, if I created a pattern, if I created a grating at one end of this side, another end of this side, right? Right? So that means only one wavelength again is possible. Now I don't need any mirror on either of sides. This acts like a mirror to me. This will allow only that wavelength which matches to this, which matches to the periodicity of this grating and periodicity of this grating. So this is called DBR laser, distributed Bragg reflectors. So these two gratings acts like a mirror, acts like a Bragg reflector, and allows only one wavelength to be processed by the active regions. So monochromaticity I have achieved. I have achieved the high output from the lasers, right? So if I see the output of this, sorry.
So how the grating is being fabricated in the material?
Uh,
Is it by etching or so?
no, no. Obviously, it is by etching or your sputtering
Material
techniques.
is the same,
Huh?
The material is the same.
Material is same. Only thing is you have structured that material in a grating pattern. You have etched that material from one end. You have created a grating pattern. It is transporting this light output. Right? Maybe tomorrow one of my colleague will be taking up such issues, Bragg reflectors or distributed feedback. So if you see the output, you see this when you increase the current, immediately after the threshold current, the output shoots up exponentially, increases exponentially, much larger as compared to LED outputs. So the current increase in current versus the change in output, power output is much larger. Okay? So till this point, you have a spontaneous emissions which is overpowering the stimulated emissions. Moment the current output, current input crosses the this junctions or knee point, the stimulated emission overpowers it. Right. So this laser threshold depends on temperature also. As the temperature keeps on increasing, the output also keep on shifting. That means if I want to work for my communication system, I must control this temperature. Right? So this is how the analog modulation, if you, in case of LEDs, if you have a output like this in the current, the light output goes like this. Same situation, you have a small current change in the laser setup, but it gives me a larger output variation in the light, right? And this is what digital is, that you are making on and off of this, and it creates a larger output at the power outputs. So when we see this output of the laser, it is temperature dependent. That means I must, while fabrication, I must, if my requirement is such that I must control the temperature, I must control the output, so that my Q point or the operating point remains the constant. That means within the setup, within the device itself, I must incorporate many other fabrication aspects. So what are those fabrication aspects? That this laser diode is mounted on a heat sinks, and at the same time we have a thermistor. We have a thermistor which monitors what is the temperature of the junction itself, right? So it monitors the temperature. If I want that this should be controlled, that 30 degrees centigrade should be 30 degrees centigrade, that means I must look for a feedback mechanism there itself. And then you have a laser diode, you have a coupling of the single mode fiber, you have a monitor diode. When I say monitor diode, the laser output also keeps on fluctuating. Maybe after 2 years, the output may not be the same. That means my Q point, if I have developed a communication system, my Q point will change. My operating point, where I look for a threshold, will change. That means I must look for a feedback, so that I can change the feedback current, so that my Q point remains the same. So that means I look for a monitor diode, a photodiode built in within the setup itself. And I look for a cooler also. That means if temperature changes to a higher side, I must look for a cooling setup wherein I can cool the junction itself. A Peltier cooling setup one can look for. Once you have such type of device, it is available. It's available. So depending on the prices one can look for, if this device one look for, then the setup, the circuit to drive this laser is looks like this, that you have a coupled to the single mode fiber, you have a thermistor, then you have a temperature control system, and then because I want a constant temperature, I must look for a cooler, so that cools the laser diodes. The output or the Q point which is coming now, after 2 years it should be same. So I look for a monitoring of photodiode, and then I give a feedback to the PN junction, so that my current which is giving the output will be maintained constant. So these are the commercial DFB lasers which are available. We also have one wherein I am using for gas sensing, where I am switching different wavelengths to monitor the gas. So these are the various parameters. What is the output? What is the forward current? What is the voltage I look for? What is the wavelength it can emit? Up to what spectral bandwidth it can produce? Then thermoelectric cooler. What is the current I can feed in maximum? Thermistor resistance. What is the resistance available to me from the thermistor? And this is the monitor photodiode current. So all these parameters within this structure, small structures, is available within the setups. So this is the comparison between LED and lasers. It has a low efficiency, it has a high efficiency, fast response times. So all those parameters which I have discussed is beneficial for laser diode. Depending on the requirement, depending on the cost, what we look for, one can monitor, one can look for whether we should go for laser, whether we should go for LEDs within the layer, whether we should go for DVR, DFBs, then quantum cascade lasers. So many varieties are available. I'm not touching all those points, but it is possible to have just one single wavelength, very sharp. Now let's switch over to the photodetectors. We have seen that the light is coming out, it is propagating through the media, or it is propagating through the some solutions or analytical systems. Now some changes has come in on the light. It can be amplitude, it can be a phase, it can be frequencies. Now I want to detect that. So I look for photodetectors which can sense what changes of light is available to me. It finds application again in electrical instruments, cameras, communication, astronomy, and SDs. The types of photodiodes which can be available in the market, they are photodiode, photodiode array, light dependent resistors, avalanche photodiodes, photomultiplier tubes, microchannel plates, image intensifiers, position sensitive detectors, CCDs, right? Varieties of photodetectors are available in the market. But from communication point of view, we have only avalanche photodiodes, and pin photodiodes. And these are for defense applications when you want to view something on the night, during nights. So again, we have to look for a requirements that it should have a high sensitivity, short response times, noise consideration that it should give me minimum noise, compatible size, that means I should be in a position to couple this to the fiber, linear response, stability, low voice voltage, low cost. The photo detection mechanism is again based on the photoelectric effect. Photoelectric effect is one which it says that if a photon is having a energy which is higher than the band gap energy or the binding energy of the electron, it can liberate that. That is what photoelectric effect is. One is external photoelectric effect, which is being used in photomultiplier tube. I will not be touching this because the course is on fiber optics. Another one is internal photoelectric effect, wherein the PN junction photodiodes, pin photodiodes, or APDs are making use of that. So, for principle of photo detection is that this we have the conduction band, we have the valence band, both are separated by forbidden band gap energy, and electrons and the valence band are bound. The electrons in the conduction band are conductive, that gives to the electric current to the output circuit. Populating the conduction band with electrons causes the semiconductor to conduct electrons. The value of band gap energy, Eg, determines the conductive properties of the materials. That means whatever the material I look for, the band gap energy defines what is the wavelength it can sense, right? So that means if I want to sense 0.9 nanometer, 0.9 micrometer wavelength, my material will be different. If I want 1.3, my material will be different. If I want 1.5, my material will be different based on the band gap. So this is what a PN junction is. You have a p doped material, you have an n doped material. This is a depletion region. When a photon falls on this depletion layer, it liberates the electron nanoholes because it has a high energy. Once it liberates electron holes, now this can contribute to the current, to the outside media, or it can recombine. Either of the two phenomena can take place. We want that the maximum output we should get, so that we get the maximum output from the current. So a PN junction can be formed by diffusing either a p-type impurity such as boron into a n-type bulk silicon. You have an n-type bulk silicon, you have doped a p-type impurity on that. So you have a p-type material, you have a depletion layer, you have an n-type layer, right? The photon which is coming in crosses these p materials, get absorbed between the depletion region, create an electron hole pair, and now this electron hole pair contributes to the current. So that means a photon is now converted into an electron hole pair, which gives me a photocurrent, right? So if by some means I get this current output, I get the electron hole output, so I can measure what is the light level available to me. So this is the PN junctions, and this is generally operated in reverse bias mode, and then it creates a electron hole pair which gives me the current output. And this is the band gap energy of the semiconductor. If this band gap energy is less than the photon energy, the photon gets absorbed. So all semiconductor photodetectors use photon absorption in depletion region to convert photons into electron hole pair and then sense them. When a semiconductor is illuminated by light having an energy E is equal to h nu, greater than its band gap energy, light is absorbed in the semiconductor and electron hole pair is generated, and this is the frequency of light. Incident photon after passing through the P region will be absorbed in the depletion layer. The absorbed energy creates electron hole pair. Electron raises the conduction band and the hole falls to valence band. The free electron travel down the barrier and the free electron hole will travel up the barrier to constitute the current flow. The photon absorbed in the neutral p or region outside the depletion region also creates EHP, but these free charges will not move quickly due to lack of strong field. There is a field exists between the depletion region because this acts like a parallel plate capacitor with positive charge and a negative charge, and there is a field exists in that. Most of the free charges will diffuse slowly, right? If we have not applied any external bias, it will diffuse slowly because it has its own velocity. These charges produce negligible current, thus reducing the detector responsivity. EHP created close to the depletion region can diffuse and subsequently be swept across the junction by the large electric field due to applied reverse bias voltage. An external current is produced, but it is delayed with respect to variation in the incident optical power. It is desirable that photon be absorbed in the depletion layer. Basically, we want the maximum absorption of the photon to take place at the depletion region because it creates electron hole pair there itself, and then when it crosses the junction, it contributes to the current. So we want that depletion region should be much wider as compared to the so typical PN photodiodes have a rise time of the order of microseconds, making them unsuitable for high-speed optical systems. We look for a megahertz or gigahertz like a setup. Then what within this junction we look for? What variety, what fabrication process, what techniques we look for? We look for. Now see this. The existence of electric field across the junction facilitated the rise of photocurrent. The primary operating wavelength region for fiber optic communication system are 850, 1310, 1550, and these are the photodetectors which are used: PN junction, pin diodes, or avalanche photodiodes. The photodetector IV characteristics under illuminations. So if we see the PN junction characteristics, it follows this formula, right? This is the forward bias characteristics of the PN junctions, and this is the reverse bias characteristics of a PN junctions, right? So what happens when light falls on it? This curves shifts slightly down when light falls on it. When further light falls, more power, it shifts down, right? So we can see this IP, the current, the shift in current is proportional to your power input, the light input, right? So this, if I plot a load line here, you can see there is a equidistance. So this is linear. So under reverse bias, it is possible to create a photocurrent using these techniques. So you see this ID is equal to I set E raised to power Q VA KBT. VA is the applied voltage. If voltage is positive, it is positive, it is exponentially decreasing. If it is 0, it is at this point. If it is negative, it is reverse saturation current, which is a PN junction diode. So I total is nothing but this current minus IP, the photocurrent, which is generated because of electron hole pair created by the photon itself. So this is the electrical characteristics, because if I want to sense this light output, which can be a modulated one, or it can be a simple light intensity also. So if in case it is a modulated one, it can be a megahertz region, it can be a kilohertz region, it can be a gigahertz region. That I must now look for the electrical characteristics of what are the components, what are the equivalent circuit of this photodiodes. So it gives me a photocurrent, it gives me a dark current, it gives me junction capacitance, because the barriers has a junction capacitance, it has a shunt resistance. The PN and N materials is giving me under the reverse bias, gives me high shunt resistance. It gives me a series resistance because of undoped region of PN junctions and the connectivity of the wires also, and then the load resistance. So this is of the order of ohms, tens of ohms. This is of the order of mega ohms. This is of the order of picofarads. Dark current is the noise which is generated within the detectors itself. So I must now consider all these parameters while making my circuit to be designed for my amplifications. So you have a shunt resistance because of which is ideally it should be infinite, but it ranges from thousands of mega ohms. This is used to monitor the noise current in the photodiode. We have a series resistance because of undoped region, which is of the order of tens of ohms. We have a junction capacitance because of parallel plates of the charge ions at the junction itself. The junction capacitance is directly proportional to the diffused area, right? Larger the area, larger the junction capacitance, and inversely proportional to the width of the depletion area. The capacitance is nothing but proportional to the area and inversely to the spacing between the two plates. So if by some means, if I want a high speed detection process to take place, my capacitance should be lower. The frequency response is given by 1 over 2 pi RC, isn't it? My R and C matters there. What is the linear range of bandwidth I can look for? So C, the junction capacitance or stray capacitance, I must minimize, right? Same with the R, I must minimize. So the junction capacitance is used to define the speed of the response of the photodiode, and the response time is now governed by a diffusion rate or drift rate or RC time constant. The three phenomena which is taking place between the PN diodes, right? So if I see this capacitance versus the reverse bias, as I keep on increasing the reverse bias, the depletion region or depletion width increases, and the separation D increases. Because the separation increases, the capacitance decreases, right? So it gives me like this, a decrease in the capacitance as I increase the reverse bias. So the total rise time is governed by T drift because of the external bias voltage I have applied, the diffusion when there was no external bias, and the RC time constant, which is based on the R and C parameters of the diode of the external parameters. So now I look for, these are the electrical parameters which I look for in the photodiodes. Now there are optical parameters, that means what is the light output, light input to the detector, and what is the output, and how it varies with the wavelength also. Okay, so it varies with the wavelength like this. That defines my responsivity. The wavelength versus ampere into watt. What is the current output per watt? So that gives me the responsivity curves of the photodiode. So the responsivity of the silicon photodiode is a measure of the sensitivity to light and is defined as the ratio of photocurrent, how much photocurrent is produced per incident light, P, at a given wavelength, which is nothing but IP by P. It varies with the wavelength of the incident light as well as applied reverse bias and temperature. It is a measure of effectiveness of the conversion of light power into electrical current. This responsivity variation due to change in temperature is due to decrease or increase of the band gap because of increase or decrease in the temperature respectively. The responsivity also varies with the temperature. The quantum efficiency defines the number of electrons emitted to the number of photons falls on them. That defines my quantum efficiency. So this is generally less than 1. So if I say 85% quantum efficiency, that means 85 electrons are produced per 100 photons falls on it. So it is related to responsivity by R lambda Hc lambda Q. And the responsivity and the quantum efficiency of different materials, because the band gap of the material defines which wavelength I can select, which wavelength I can sense. Like for silicon, it is up to 1.1, that means up to 1100 nanometer I can sense for silicon. For indium gallium arsenide, I can sense up to 1.7. For germanium case, I can sense up to 1.6, ranging from 0.9 onwards. So quantum efficiency and responsivity curves gives me which material, which photodiode I look for based on the wavelength region I am working for. So quantum efficiency is not constant at all wavelengths, varies according to photon energy. For a given material, as the wavelength of the incident photon becomes larger, the photon energy becomes less, because when you go higher and higher, the energy of the photon becomes less than the rate required to excite an electron from the valence band to the conduction band. Responsivity falls off rapidly beyond cutoff wavelength. So now question comes, once you have a photodiode, which is just a PN junction, we know that it produces electron hole pair, which is giving you a photocurrent, and now this photocurrent I must sense it. One way is using a photovoltaic mode, wherein I am not using a high speed communication system. A small up to kilohertz I can sense, or a light photometer if I want to make. I can use no biasing setup. I have not biased it. The PN junction or the depletion region, the electron hole pair produced by the photons are diffused because of the electric field available at the depletion region itself, right? So that electric field, that photocurrent which is produced, is passed through this resistance, which is very high, of the order of 500 mega ohms or so, and now this current is multiplied with this resistance, gives you a photo output, a photocurrent output, right? So this photovoltaic mode is being used when I am not looking for high speed operations or a linear operations like in photometers, wherein I want to sense the light outputs. The frequency band operation is governed by RF and CF combinations, just to avoid the gain peaking at the amplifier points. Another area is photoconductive mode, wherein I can use a reverse bias. When I use a reverse bias, that means my depletion width increases, my capacitance decreases, I can operate at a much higher frequency range, isn't it? So there is an increase in depletion region, there is a decrease in junction capacitance, increase in dark current, there is an increase in dark current in this case situation, but I must look for what are the techniques I have to decide, so that I can reduce the noise there. And then there is a decrease in rise time because capacitance decreases. A feedback capacitor will limit the frequency response and avoids gain peaking at the amplifier output. I can amplify further on that. And then there are noises within the detector itself. There is a short noise because there is a electron hole pair produced, and they are random. No. It may lead to a photocurrent, it may not lead to a photocurrent. It can recombine itself. So this short noise is related to your photocurrent itself, and this is governed by the bandwidth also. Larger the bandwidth, larger the short noise. And then the thermal noise, the shunt resistance, which is of the order of mega ohms. Each resistance has its own thermionic noise associated with it. So I must look for I junction, I shunt resistance, which is governed by 4 kb T delta F RSH. Now if I want to reduce this noise, I must limit my delta F, I must reduce my T, I must increase my RSH, shunt resistance. So all resistance have a Johnson noise associated with them, including the load resistance. So all these resistances which we use leads to the noise there itself. Now there are various figure of merits when we look for a photodiodes. What are the parameters I look for to compare which diode is better? Which one I should select? So one is noise equivalent power. That means what is the minimum noise a photodetector can produce. It is governed by noise equivalent power. That means when S by N is equal to 1, signal power or the photo current to the noise power equals 1. That means what is the minimum noise level it can give? It gives me noise equivalent power. Then comes the detectivity, which is 1 over the NEP. Then comes the specific detectivity, which is nothing but because photodiodes are available with a different area. It can have a larger area, it can have a smaller area. Like I say, capacitance is proportional to area by the spacing between the plates. So smaller the area, smaller the capacitance, isn't it? So if I want to work for a high speed, I should look for a smaller area photodiodes, right? Within this smaller area photodiodes, I must look for what is this NEP of that, specific detectivity of that area, and detectivity gives me this specific detectivity so that I can compare. Larger the specific detectivity, better the photodiode, right? Now, as I said, PN junction, you have a depletion region which is very small, and the photons are to be absorbed in the depletion region itself. So what I look for, my depletion region should be much wider. In that situation, if I create an intrinsic layer itself, if I create a p material, N material, and intrinsic layer or depletion layer to be much wider, then it is possible that my most of the photons are absorbed in the depletion region, and then electron holes which are produced here, they can traverse to the respective junctions to create a photocurrent out of it. So a new photodiodes, which is called pin photodiodes, has come in, wherein intrinsic layer has been incorporated in this, right? So this is what is called pin photodiodes. So the bandwidth can be extended to tens of gigahertz. I can use a reverse bias to operate this. So it has a highly doped transparent p-type materials and n-type highly doped contact layer on the bottom. We have a larger depletion region. A advantage is that the recombination generation time constant is longest for the undoped material, which provides a minimum thermal generation currents. Once we have a pin photodiodes, another situation comes. Can I see? One is that whatever the current which is produced, I use a larger resistance to get me a output, because current into resistance gives me the voltage. If my current is microampere, then I used a mega ohm of resistance. Now this mega ohm of resistance gives me an amplification which gives me around 1 volt or so, right? So can I look for a photodetector which has an internal gain itself, right? So that situation comes when you have a avalanche multiplication within the setup itself. Suppose you have a PN junctions. Now I produce a reverse bias which is much larger, so that the electrons which are produced because of photocurrents gains enough momentum while moving to the respective junctions. They attain enough kinetic energy to bombard the silicon lattice or the lattice of the p-n or end sites. So when they have the enough kinetic energy, they can liberate further electrons. So one electron liberates further electrons, leads to a amplification within the photodiodes. So think of a situation that you have an n-type material, you have p-type materials, you have an intrinsic layer, and then you have p-dope material again. This is the absorption region where photons are absorbed, created a electron hole pair. Now you have applied a high reverse bias, and this electron hole pairs, while traversing to the uh, respective junctions, uh, gains enough momentum to liberate further electrons, and then there is a gain mechanism within the this region itself, because the high reverse bias exists at this point. So it creates a multiplication effect here itself. That means one photon gives me somewhere around 10 raised to power 4 of electrons. So that means there is a amplification within the setup itself. So photodiode will internally multiply the primary signal photocurrent before it enters the input circuitry of the amplifier, increases receiver sensitivity, but somehow the noise also increases. And this is called impact ionations, and this effect is called avalanche effect because of the high kinetic energy. The reverse bias which is used is of the order of 100 to 400 volts, and the carrier multiplication of the order of 10 raised to power 4 can be achieved. That means one photon gives me 10 raised to power 4 electrons in the system. So when we use such a device, such a detector, I don't need a amplification at the op-amp levels. So when carriers are generated in the undepleted material, they are collected somewhat slowly by diffusion process. This has the effect of producing a long diffusion trail on a short optical pulses. Basically, we want that the light is to be absorbed between the depletion region, right? And then it is to be multiplied at the gain region. So that the structure of the PN junctions can be modified, or APD can be modified to achieve this phenomenon. Right? The response time is again governed by the transit time of the depletion width. Again, the avalanche multiplication also takes some time, the RC time constant. All these parameters one must consider while designing the amplifier setups. And this is the multiplication factors Im by Ip. What is the input current and what is the amplification factor, which is of the order of 10 to the power 4. Not all photocurrents experiences the same multiplication factor. So that means there is a randomness in the multiplication itself. There is a randomness in the output itself, right? And that leads to some noise phenomena within that setups. So we have an advantage that there is an increase in the sensitivity. There is a large dynamic range. That means I can sense a lower value to the higher values. But there are drawbacks. There is a difficulty in fabrication. There is a random nature of the main mechanisms. High voltage is required. High voltage is required. Right. So these are the some of the APDs and photodiodes which are available in the market. These are the silicon, range is this, germanium, range is this, indium gallium arsenide 900 to 1700. Then the peak wavelengths, and then the responsivity, which is 0.6 for silicon pin case, it is 130 for APD case. That means the responsivity is much higher in that case. For indium gallium arsenide, it is 0.63, 0.8. Then quantum efficiency is around 90%. For germanium case, it is 55, and indium gallium arsenide, it is 75, 70%. Then again, dark current is also very important while making for uh, our amplification factors, capacitance, the amplifier, price time, all those things one must consider while designing this. So with this, I thank you all. So if you have any